Okay, my screen is visible. Anybody?
Yes, sir.
Okay. We'll see today RLE load. So yesterday's class we observed single phase half controlled rectifier. That is a half wave controlled rectifier. If you want, you can modify like this. Half wave controlled rectifier. So R load we noticed, and RL load and RLE load, this one. So the difference between these things are, it is nothing but a motor. RLE load is nothing but a motor. Means armature resistance, armature inductance, then back EMF. That is nothing but a battery. That's why equivalent circuit of a motor we can represent like this RLE load. Now this is the circuit. We start with R load yesterday, and then we added L. And one thing we noticed, R load and RL load, let it be as a supply, and this supply, and for R load waveform you can see like this. Start with alpha, end with pi. For this circuit I am writing, and the negative of cycle 0. This is for R load, and similarly RL load, we start with alpha, end with beta, and then it will be 0. So beta R and pi plus alpha. If it is a beta less than pi plus alpha, we call it as a discontinuous mode. Is equal to pi plus alpha, it is a continuous mode. Now in the RLE load, only the different you can notice here, the device will be turned off at 0. I mean beta R at pi, and after that the magnitude is 0. And now if the device is open at this instant, if the device is turned off, then if I measure voltage across this, what I can get? It's not the 0, because we have something battery here. It may be any volts, it may be 100 volts, 50 volts or whatever. If I measure when the switch is open, means it is open at beta or a pi plus alpha or whatever the instant, and once switch is completely open, what will happen? Load is isolated from the source. In the previous R load and RL load, we don't have any battery in the load side. That's why voltage will be 0 after switch is open. For R maybe at pi, and RL at pi plus alpha or maybe beta, depends on the inductor value. If I use large inductor, it will store more energy. To dissipate that energy, it will take more time, up to pi plus alpha. That is the difference between continuous and discontinuous mode of operation. Anyhow, it will be clear for the next slides. At moment, because only one thyristor, it is not possible to see current is remains 0 or not. But if it is a full wave, we have two thyristors, continuity is there or it remains 0. If it remains 0 some duration, it is a discontinuous mode of operation. And if it is continue to conduct pi plus alpha, immediately next thyristor will conduct up to 2 pi plus alpha, then next, like that, we call it as a continuous mode of operation. So now in this RLE load, battery is present even though the device is turned off at beta, and it will be remains, it will not be 0, it will maintain whatever voltage will be present in the load side. So that is only the even wherever off state will be there, it will be turned off and it will maintain like this. So this we call it as a back EMF. Whatever magnitude I shown here, that is a E or a battery voltage or a back EMF voltage. So earlier waveforms and this waveforms are like this. The difference, what you want to do is you just find the differences only, because the derivation part everything is same. Only limits will change, no? For C, R load will start with alpha to be pi, RL load alpha to beta, and this one alpha to beta 1 instant Vm sin omega t. From there onwards, it will be as a E. So that you can add it. So that will give as a expressions. Now we'll see the waveform. Now the same logic, only one thing, additional thing you need to notice here. Carefully you observed here. So I mentioned there is a theta 1 here and theta 2 here. In the case of whether it is R load or RL load, the device will start conducting from alpha is equal to 0 onwards. It is possible. Once if you give the firing pulse, it will be forward bias and it will conduct. But in the case of RLE load, what will happen? You can see that. Suppose if I give firing pulse before theta 1, I mentioned theta 1 instant here. You can see this line, horizontal line, it is a battery voltage or a back EMF voltage, and that is touching this point at supply. That I call it as a theta 1, and this side I call it as a theta 2. So now theta 1, this is the instant of theta 1. We can observe the thing before theta 1. Before theta 1, what will happen? The supply voltage is less than the battery voltage. So if that is the case, what will happen? Thyristor is the reverse bias. Even though thyristor anode is connected to positive, but cathode also connected to positive in the load side. So load side is there is a battery. And now when it will become forward bias, the condition is when our anode more positive than cathode, then the thyristor will be forward bias. That is the instant. But now what will happen? You can notice the thing. Before theta 1, anode is less positive than the cathode. That's why thyristor will not forward bias. Even though if you give the firing pulse, it will not trigger, because it is a reverse bias. So that is the reason we can see the instant at theta 1. At theta 1 onwards, both magnitudes are same, and from there onwards, what will happen? Supply is more positive than battery. That's why we should not give the firing pulse before theta 1. Same logic is applicable for the second side, that is a theta 2. After theta 2, what will happen? Again, supply magnitude is less than battery. So that's why what we can do is after this point of theta 2, this magnitude is, supply magnitude is less but battery magnitude is more, then also reverse bias. So from this analysis, what we can conclude is firing angle range is limited here. So we want to control the output voltage between theta 1 and theta 2 only. You have to fire the devices. That is the clarification that is based on your input supply and battery voltage. So that is what theta 1 and theta 2 we mentioned. So now after theta 1, you have to give the firing pulses. Once pulse is given, the remaining operation is as usual. So once the device is turned on, then what will happen? You can see here, if device is on at alpha, that you remember that alpha must be greater than theta 1 and less than theta 2. So these are the instants based on the battery voltage. Suppose if battery voltage reduces, this one is reduced, then we get like this. No? Now the point of theta 1 is here and theta 2 is here. So wherever it is touch that line, supply line, that we call it as a theta 1 and theta 2. So now, so in that, in general word, I can say that firing angle range is between theta 1 and theta 2. So now I given alpha at an angle of some degrees, it must be greater than theta 1, and it starts conducting and giving pulse to the thyristor 1, automatically thyristor will start conducting. Then what is the load voltage? load voltage same as the source voltage. So what is the source? You can see from this onwards it will be same as the source voltage. It will not turn off at pi. That also point because of the inductor present in the load. Then what you have to do? That will continue to conduct based on the inductor value, that will continue to conduct whether it is up to the pi plus alpha or a beta. So now let it be considered if it is a beta. So this the beta instant.
Leave 10 mm. So this will be your very thin line.
Now we can see this is a beta point. So at that point, whatever energy is stored in an inductor, that is going to be dissipated in the same thyristor, and energy will be completely dissipated, and then what will happen? Device will be turned off at beta. So that is the point. You can see that up to that the same as the source voltage. It will continue to conduct up to beta, then output voltage same as the source voltage. But now we can see after this instant, the device is turned off, this will be open, and then load voltage is same as the battery voltage, because this is open. No, whatever voltage is present here, that will be represented as a load side. So that's the reason this will be maintained in the same as the battery voltage. Whereas in the RL load previous waveform, what we'll do? We'll make it as a 0. That's all the difference. Because there is no battery, once the energy is completely dissipated, thyristor will be open. If thyristor is open, across load will be 0. That's why we make it as a 0 in the RL load. But now in the case of RLE load, what I have to put it? Whatever battery voltage is there, up to that. And next, negative half cycle, it is 0. No, thyristor will be open, so it will be represented same as the battery voltage. How long? Next thyristor will fire. When the next thyristor will fire? Again next positive half cycle. Next positive half cycle again at 2 pi plus alpha. Whatever alpha we are maintaining, that we can place again firing pulse. Wherever positive half cycle is there, there you can represent the firing pulse. Again thyristor 1 will or thyristor will conduct. It will give same as the source voltage. So that will be the procedure, and next negative half cycle will be remains 0. The next positive half cycle 4 plus alpha, thyristor will conduct. Like this cycle is going to be repeated. Current also same, it start with 0, rises up to the pi. From pi onwards I am representing in the downward direction, or let it be dropping. What is the reason current is decreasing? Because up to pi thyristor is conducting in this way and inductor is charging plus and minus. That's why current will be gradually rising, because inductor store the energy, current will be gradually rises. But after pi, what will happen? You can notice that the after pi supply is negative. So that's why normally the thyristor must be off. But there is energy available in the inductor. That energy has to be dissipated. For that reason, that thyristor will continue to conduct some more time, but whatever energy stored in inductor is going to be dissipated. That is the reason it is the decreasing order. Once the energy is completely dissipated, that means that current is 0. So if current is 0, the thyristor will be open. So that is the reason for all the cases RL loads and all, you notice the current waveform. Current waveform obviously rises from 0 onwards, or let it be alpha onwards. At that instant only thyristor will starts conducting. From that point onwards, current will be gradually rises up to pi only. It is not beyond the pi. Up to pi it will rises. From pi onwards, whatever energy stored in inductor, that is going to be dissipated. So the dissipation time, gradually current is going to be decreases. So that is the reason always I will represent in the RL load case, current will be gradually rises up to the pi, and then it will be decreases gradually. So now we can see voltage across the device. So now voltage across the device, we can notice one thing, start with alpha and then how long the device is conducting, that portion you make it 0, and after that device is turned off and the voltage across the device, it will be the same as the source, but here there is a additional voltage source also present. That's why Vm plus E, that will be as a peak inverse voltage. So whereas in the earlier peak inverse voltage we noticed that Vm, because whenever device is in the off state, voltage across that device will be the reverse voltage appear across that. No, that is a peak or a maximum inverse voltage is a Vm. But in this case, there is additional voltage also will be present here. That's why Vm plus E, that is the total voltage applied across a reverse direction in the thyristor. So as usual, again this logic is same. Whenever device is conducting, then voltage across the device is 0, and when the device is off state, then the voltage across the device same as the source. That logic, but source is additional voltage is also there, you can represent that. So now we can see that what is the value of theta 1. Theta 1 is nothing but a sine inverse E by Vm, or sine theta 1 is equal to E by Vm. So that is the value of theta 1. So always your alpha must be greater than the theta 1 and also less than the theta 2. So otherwise what will happen, device is reverse bias, the device will not conduct. So that is the instant we must remember, theta 1 instant. And as usual, you can represent the voltage equation when the thyristor is triggered. Voltage equation is Vm sin omega t, as usual supply. In the case of RL load, what we mentioned, R into I naught, yesterday's derivation only, same what we derived for the beta expression, no? Same fashion here also. Input is Vm sin omega t, that is equal to R into I naught plus L into di by dt plus E. Whereas RL alone, you can make use R into I naught plus L into di naught by dt. And from that we find that I naught is equal to Vm by Z into sin of omega t minus phi plus something constant into e power minus R by L into t. That is the steady state and then transient condition. You can add it, you will get it as a final total current in that expression. Similar fashion, here also additional parameter EB will be there or E will be there. So steady state as usual, Vm by Z sin omega t minus phi, and then another steady state also there because of this back EMF, that will be minus EB by R, and transient condition something constant A or K, anything you can use it, d power minus R by L. That is into T, that is the expression for now the total current or I naught current, sum of these three, to steady state plus transient. So now again substitute the initial conditions and find the A value and we'll get the expression. So that way, that same derivation, that's what I told now. If we start with half wave rectifier with R load derivations and the theory as well as the waveform, only slight one step modification, not more than that. You can see R and RL load, negative will get. RL and RLE load, there is a during 0 instant you will get it as a battery voltage, like that. So that small difference you remember, it is easy. And now I added all the three, we will get it as a I naught current. Now to get the constant A, what I substitute there, same again, omega t is equal to alpha, current I is equal to 0. Now also I substitute that omega t is equal to alpha and t is equal to alpha by omega, and current I naught is equal to 0. Therefore 0 is equal to, you can write, that's what limits you can see, omega t is equal to alpha, current I naught is equal to 0, because our waveform is like this. See that our what we call it as something we start at alpha, then it will getting like this. So now we started at alpha and then maybe beta or pi plus alpha. This is a voltage waveform. Current waveform start with alpha, rises up to pi and then decreases to beta. So this is the current expression. So this second one is a current and first one is a voltage. So using this, you can see that. So using these two waveforms only, we are substituting the initial condition. See that omega t is equal to alpha. What is the current? 0. So that's why that is a first initial condition. So you can get it A value. And then same thing you can substitute it in I naught. and you can further initial condition also you can substitute omega t is equal to beta and current I is equal to 0 like that, and we can get the current waveform. From that you can see that voltage waveform and current waveform is slight modification, and now divided by r if we give we'll get it as a current. So limits are alpha to beta only. You can see in our case limits alpha starting ending will be beta, or if we keep that beta replaced by pi plus alpha, that we call it as a continuous mode of operation. So that is only the different, and if you just integrate that limits we'll get it as a final expression of current. So now you know the gamma, gamma is equal to beta minus alpha as per this waveform. You can see again this waveform, it is starting alpha, this portion is a beta portion where it is 0 instant, and then gamma portion is this one from alpha, this starting point, and this is ending point. So this one is a gamma. So only I want gamma means what? Total beta minus this alpha. It is a where it is delayed now. So beta minus alpha will give as a gamma. So from the expression it is very clear, you can see that total is beta, and only conduction portion I call it as a gamma. Gamma is nothing but a conduction angle. Beta is nothing but extension angle or extension to current to 0. That instant I call it as a beta, and alpha is a firing angle. So now from this you can say that gamma is equal to, you can write gamma is equal to beta, total is beta minus alpha. So that will give as a gamma. That's what we mention here. So gamma is equal to beta minus alpha, and just simplification. Again it will be as a cos A minus cos B form. They simplified further, and finally we'll get it as I naught expression. And load voltage. So V out or a VDC. Here in the earlier version and this version little bit different, because there is a back EMF will be there. Output voltage is equal to whatever drop output current passing through the inductor and plus back EMF, that is motor equation. I told no, it is equivalent to motor in machine 1 and all. In DC motor, how will you write the VA armature voltage, that is equal to EB plus IA RA, no? That is armature resistance, armature current. That is the expression for motor expression. Now also it is indirectly we connected as a motor, or you want directly you can use as a motor symbol also in the drive subject, there we will use it. At moment V out is equal to EB plus IA RA fashion, and I naught we already derived, and R is just multiplication of that. RR will get cancelled out because in I naught expression there is a R will be there, no? So E as such plus I naught into R and R will get cancelled out, 1 by 2 pi into rest of things will give as a V out. And similarly, we can another way also you can represent the expression directly alpha to beta. Alpha to beta Vm sin omega t plus Eb, and that integral. What is the limits? You can, if you want, you can one more step. You can write like this: V out, that is equal to 1 by 2 pi as usual. This is common, and now first limit is alpha to beta Vm sin omega t. So this Vm sin omega t, and plus another instant is what? From beta to 2 pi plus alpha. What is the output? E, only back EMF. We close it. That's all. So that only after doing this we'll get this point. And you can simplify this. Final expression is 1 by 2 pi Vm cos alpha minus cos beta plus Eb into this 2 pi plus alpha minus beta. So here you can see that instead of directly specifying that, you want, you can use like this beta starting point and 2 pi plus alpha interval, you can make it. Only you can use E. This can rough E into d omega t. That's all. If you do that, we will get it this expression. So this is the voltage expression by make use of this way with the back EMF. And what are the disadvantages of a half wave control rectifier? So one thing we can clear that current waveform is not in the form of straight. DC means what? It is a straight line, no? But what we are getting as a large pulse ripples, and then it's not smoother. And output also very less output we are getting. And another one we can notice that during negative off cycle we are not getting any output, no? Because only one thyristor. Another name for this also, you remember all of you, it is a one pulse converter. In exam, indirectly they ask the question, explain one pulse converter with R load or maybe RL load or RLE load or RL with freewheeling diode. That also yesterday I explained. There is a two ways. See, the answers are very similar. Only thing is you identify what portion you want to write. The one question is explain half wave controlled rectifier with R load or RL load or RLE load, anything. Another question is explain half wave controlled rectifier with freewheeling diode. And another one is explain significance of a freewheeling diode. In that case also use this circuit with parallel with the diode. Yesterday, last topic, we noticed that RL load with freewheeling diode. And you write the comments, what is the advantage of freewheeling diode. Output will be improved compared to RL load, and current waveform will be improved, power factor will be improved, and negative conduction will suppressed. So we are not getting any negative voltage once if we connect as a freewheeling diode. Otherwise, what will happen? We are getting after pi, no, device will continue to conduct, we are getting as a negative voltage. So that is the things. So questions, answers are same but different way they, and otherwise they may ask that explain a one pulse converter with RL load. One pulse converter means that is nothing but half wave. That is the reason I mentioned the classification earlier slides, whether it is a based on the pulse or based on the quadrant and based on the supply, all the things I mentioned there. So one pulse converter is nothing but a half wave rectifier. Two pulse converter is a full wave rectifier. Three pulse converter is a three phase half wave rectifier. And six pulse converter is a three phase fully controlled converter, like that. So these are the based on the pulse number. Pulse number is very simple logic. One full cycle of AC supply, how many pulses we are obtaining in the output, that is a one pulse converter. That's all. So now if you want to make it like this, this is a one pulse converter, we are getting one output, next will be 0. And two pulse converter, one full cycle of AC supply, input is AC. You can see on to convention, input is AC supply, you are getting as a one pulse in the output. Input is AC, you are getting two pulses in the output, that is a two pulse converter. And three pulse converter, you will get three pulses, your input is three phase supply, you can write like this, three pulse converter. Six pulse converter means you'll get six pulses in the output. So that means by observation, you can see that by increasing the pulse number, waveform will be smoother. Finally, it will get it as a straight line in nature, and discontinuity also will reduce. So like this. So these are the pulse number. So the definition of one pulse converter means one full cycle of AC supply will obtain only one pulse in the output. That we call it as a one pulse converter, or to obtain two pulses, two pulse, like this. So now we can see the some of the disadvantages. One is what? Low DC output voltage and lower efficiency, because we are getting only one pulse in a output. During negative off cycle, you are not getting any output. That's why low DC output voltage. Then another one is a high ripple voltage and ripple current, because the it is not in straight line in nature, ripple will be more. And then higher ripple factor, same thing, we already derived no form factor, ripple factor expressions. So that from that form factor is RMS by VDC, and then ripple factor is root of form factor square minus 1. That means, so that factor will be high. On low transformer utilization factor, obviously, because the transformer utilization, when you are using as a transformer, if you are not properly operating, only you are drawn power from the source during positive off cycle only. During negative off cycle, the transformer is isolated from the load and source. That's the reason we are not utilizing properly the transformer. So that's the reason you can say that low transformer utilization factor. And then rarely used in a practice as they given low DC output power. So this will be rarely, because all these drawbacks, generally we don't prefer this half wave rectifier. It is after all very small amount and to large ripples, so you cannot operate as a machine or anything. So that's why generally we don't use this. And now the next one is a full wave rectifier or a fully controlled rectifier. Now there is a two, you just remember the classification. First one is half wave, second one is a full wave. In a full wave, we have what you call it as a midpoint and bridge type. So the midpoint we will see now. Then next class we will see the bridge type. In a midpoint, we can see same. What we used here is a transformer. So that is the problem between the midpoint and then bridge type. So bridge type, this transformer is not required. And whereas midpoint or center tap, both are same. M2 converter, another name for this is a M2 converter. You just remember all these names are different names. There is a 2 pulse converter. Another name for this is a 2 pulse or M2 converter. M means midpoint. Suppose if I explain bridge type B2 converter, that means bridge type 2 pulse converter. 2 represent the pulse. So M2 midpoint 2 pulse converter, B2 bridge type 2 pulse converter. So this is the convention. You just remember that way also. So that's the reason I mentioned M2 converter is a midpoint 2 pulse converter. And full wave controlled rectifier. What is the different half wave and full wave? Only one pulse in the half wave, and full wave 2 pulses. That means 2 thyristors are there, 2 pulse converter. Now by seeing the circuit and waveform, I don't think so the explanation is required. You just recall previous explanation of half wave rectifier. What is that? Exactly same, only the difference is during negative off cycle. So in the case of half wave rectifier, I will draw the circuit for half wave rectifier in the previous one. Just I am directly giving supply. If you want, you can use transformer also. Only one thyristor connected to load. That's all. This is the circuit. And for this circuit and the waveforms in the previous, this portion waveforms are absent. It will be 0. Now it will be present because the during negative off cycle also one of the thyristor is a forward bias. That's why it is conducting. It will appear. Then the total output voltage will be doubles than the half wave rectifier. Half wave rectifier only positive off cycle. So now we can remember this. The logic is very simple. During positive off cycle, explanation for all these controllers in this unit, only 2 steps. One is during positive off cycle, you write it, and then next para is during negative off cycle. So now you see during positive off cycle, what will happen? This is a plus. It is a midpoint, remember, it is a plus and minus because center tap transformation ratio 1:1. You can see each secondary to the primary is 1:1. Now whatever magnitude you are obtaining here, that is Vm sin omega t only. Vm sin omega t. Same thing will be appear here also. This is Vm sin omega t. So both is Vm sin omega t. So midpoint, so same taps. Tap ratios are secondary to each secondary to the primary is 1:1. Now during positive off cycle, which devices are forward bias? T1 alone forward bias. So during negative off cycle, T2 will be forward bias. So that's the reason we can see that how the current is going to pass. So during positive off cycle, this will be plus, this will be minus. So now current is passing through T1, it goes to R. That is a during positive half cycle. So now in this instant, output is what? Same as the upper winding. What is upper winding? That is Vm sin omega t. So output is same as input only now. Whatever it is shown, that will be represented in the output side from alpha onwards. So now I given pulse at alpha. Thyristor T1 will starts conducting. Current will pass a T1. If you want, you can put it some point here, just for remembering, or O point or anything you can give. Then current direction will be A. It goes to the T1, then O, then R, then neutral. That's all. So this is the current direction passes through the thyristor. So the reference direction and this direction is same, current is positive. That too I used as a resistive load. Then what will happen? Voltage and currents are exactly same. Only magnitude you can reduce. Up to this is over. During positive off cycle, thyristor T1 is forward bias at an angle of alpha, or at omega t is equal to alpha. We are given firing pulse to the thyristor T1. Thyristor starts conducting from alpha onwards. Then the load is directly connected to source through thyristor T1. Then the load voltage is equal to the source voltage, and load current also equal to the same shape, but magnitude is reduced by R. And then voltage across the thyristor 1. What will happen voltage across thyristor 1? Because it is conducting from alpha onwards, voltage across the thyristor is 0. And 0 to alpha, thyristor is off state. That's why voltage across the thyristor 1 is same as the source voltage. Source is a supply. This one you can represent the VT1. The rest portion it will be 0. Then what about VT2? VT2 is open, no? Voltage across thyristor 2 is open. This is directly connected up here across the source. So that is the reason we can see that you can make it as a same as the source, but the polarities are reversed, no? This side is minus, you are getting as a minus. So this is the case of VT2. Now first portion is over. So during positive off cycle is over. And during negative off cycle, then this thyristor T1 is going to be turned off at pi due to natural commutation. The reason is current also will be 0 at pi, because resistive load, voltage and currents are in phase. Therefore current also will be 0 at pi. That is the reason thyristor is going to be turned off at pi. Then pi to pi plus alpha interval. So over up to this pi. And then next is what? Pi to 2 pi interval, which is a negative off cycle. So pi to 2 pi is a negative off cycle. So thyristor T2 will be forward bias, not a conduction. You remember the different? Conduction means whenever pulse is available, then it will be call it as a conduction. So if pulse is not available, then I call it as a forward bias only. So now we can see from pi to pi plus alpha, the thyristor has to wait, because we are giving pulse only at pi plus alpha. So during negative off cycle, T2 is a forward bias. At omega t is equal to pi plus alpha, thyristor T2 starts conducting, because we are passing the firing pulse. Once thyristor T2 is conducting, then what is the current during negative off cycle? Means this is minus, this is plus, no? Now current is passing like this. Write the point B, T2, O and R, then N. So that is the current direction. Therefore, what will happen? Thyristor is conducting from pi plus alpha to 2 pi. Again, supply will be 0 at 2 pi, and current also 0, load voltage also 0, and thyristor T2 will be turn off at 2 pi due to natural commutation. And from 2 pi to 3 pi, again T1 will be forward bias, and at 2 pi plus alpha, thyristor 1 will conduct and cycle is going to be repeated. That's all. So this is the way we can explain simply M2 converter with R load. Now the derivation, everything is same, only one point is different limits. And that too, one more thing is 2 pulse converter. There earlier it is a 1 pulse converter, 1 by 2 pi we used the formula. And here is a 2 pulse converter. Instead of integrating 2 times, what I will do is magnitudes are same, no? Alpha 2 pi interval, you can see this is starting at alpha, ending at pi, no? This magnitude and pi plus alpha to 2 pi magnitude is same. So I want to integrate up to 1 full cycle. What is 1 full cycle? Up to 2 pi. In a 2 pi, we obtain 2 pulses in the output. So 2 times integration is waste of time. So what you will do is just one pulse we are integrating, multiply by 2. Then the limits are what? Alpha to pi only. But instead of 1 by 2 pi, you make it as a 2 by 2 pi. Limits are alpha to pi. Output is Vm sin omega t. You will get it directly as average output voltage of controller. Obviously, it is a doubles that of a previous one. So previous one only one half cycle, and now we are getting as a two positive half cycle are getting output, negative half cycle also are getting output. So obviously output will be double. And another one, I mentioned this is a one quadrant converter. Remember one thing, for all the resistive loads, controller, any controller, if it is a resistive load, it will operate only in the first quadrant operation. Whether you call it as a full control rectifier or a semi converter or anything, if it is a resistive load, our quadrant operation is always first quadrant, or also called as a rectification operation. What is meaning of it? In this waveform you can see that what is voltage? All positives only. We are not getting anywhere in the negative. So if you take average of this, will give positive. Current also positive. Then if you take product, so because power will give as a positive. Voltage is positive, current is positive. It is a first quadrant. That's why you mention here voltage is positive, current is positive, then it is a first quadrant converter. So first quadrant converter means voltage is positive, current is positive. So that is the reason it is a rectification mode of operation. What is meaning of rectification? AC to DC. So input is AC, output is a DC. So rectification, power flows from AC to DC. That I call it as a rectification, or also called as, in terms of the drive aspect, we call it as a motoring operation. So this is the case we can represent it is a rectification. Now after that, these things are well known to you. Whenever it is on, we can see that make it as a 0, or short means 0. So this will be on during T1 is on here, T2 is on here, again T1, then T2. So this instance you make it as a 0 for T1. Wherever T1 is there, you represent that will be 0. Here is you can make it 0, and wherever T2 is there, here we make it 0. Like this, you can get it as a rest portion same as source, and this is a source is positive side with respect to anode. No, here source with respect to negative. That's why we'll get it as a negative. That's all. So this is the R load. Now, what we can get it? Expressions. So our derivation, you can see that what is the average output voltage as per our previous explanation. Simply it is a 2 pulse converter, 2 by 2 pi, limits are alpha to pi, output is Vm sin omega t. So that if you do, integrate it, what you can get? Vm by pi integral 1 plus cos alpha. Now you can see in the case of previous one, R load half wave case, Vm by 2 pi into 1 plus cos alpha. So that is the difference between half wave and full wave. So this is a Vm by pi into 1 plus cos alpha. This one is a Vm by 2 pi into 1 plus cos alpha. So we are dividing by 2. That means half of is reduced in the half wave, and full wave will be doubles of this. So this is the expression for average output voltage. So what is average current divided by R, and RMS? What you will do the RMS case? Just Vm square sin square whole power 1 by 2. Like this. Again same 1 2 will differ there also in expression. So now you can see this is a Vm by pi into 1 plus cos alpha, and maximum output voltage, put it alpha is equal to 0, then cos 0 is 1, that means 2 Vm by pi. That is the case of maximum output voltage. And then average output current, this divided by R, that will give as a current. And then RMS, the same expression, only Vm square sin square omega 2 whole power 1 by 2. And here you can see that previous half wave expression and this expression, in that case this denominator factor is a 4 pi, and here is a 8 pi. In case of what we call it as half wave. That's all the difference, because only 2 is the problem, because 2 by 2 pi, no? So that is the difference. Now we can see that all the derivation remaining, all the things PDC, PAC, form factor, utilization factor, power factor, everything is same formulas only. Only different expression is this one and is this one. This is the voltage VDC and VRMS is this one. So remaining is as usual formulas. If you want, you can make it IRMS is VRMS by R, power delivered to the load, just and output side load power PDC, and power delivered to the load VRMS into IRMS, everything same as that formulas. Efficiency PDC by PAC, and power delivered to the load by volt amperes, that means VRMS by VS, and like this form factor, ripple factor, only the formulas, transformer utilization, all these things. Now we'll go for as a RL load. So what is the difference between R load and RL load? So it is very simple logic. Wherever it is a 0 in case of R, there you make it in the load side, I am telling, you will get it as a some negative, because instead of turn off at pi, the logic is again only you can easily remember waveform, simply supply like this many number of cycles, and we are giving firing pulse somewhere at an angle of positive of cycle you have to give it, and negative of cycle also you have to give, because it is a full wave, no? This is for negative of cycle, this is for positive of cycle, this is supply, then Ig1 for thyristor 1, meaning Ig2 gate pulses for thyristor 2, and 0, pi, 2 pi, 3 pi. So this way you can make it as a output. Now we'll see if it is a resistive load. I will make it like this. At pi plus alpha, next thyristor is conducting, and then at 2 pi plus alpha, next cycle is going to repeat. That's all. So this is the case of output voltage for R load. Now RL load, what will happen? Why this gap? Actually, because the device is turn off at pi. That is the case of what you call it as R load. So R load case, due to natural commutation, it will be turn off at pi, 2 pi, 3 pi, and so on, because voltage and currents are turn off naturally. Voltage is 0 and current also 0 at pi, then the thyristor T1 will be turn off. So now what I want to do is, instead of turn off at pi, because of inductor, the circuit is having as inductor. Now what will happen? During positive cycle it will store energy, during negative cycle it will be minus and plus, so that will continue to conduct in the same thyristor. If the device is conduct after pi, what is the supply? Same as negative, no? This is the supply, how long it will be conducting. Suppose if it is a continuous, then it will be conduct up to like this. Similarly for next device, over, and this side also repeating the cycle. So this is the waveform for RL load, over. If it is R load alone, whatever I drawn the red color, after pi it will be 0, and pi plus alpha next device will conduct. That will be as a R load voltage waveform, and current waveform same as the voltage waveform only for the resistive load. Now for RL load, there is a two modes of operation. One is a continuous mode, another one is a discontinuous mode, as well as the rectification mode of operation, and then inversion mode of operation. So we'll see that. At moment, we'll see the rectification mode of operation. RL load, the device will not turn off at pi, because some energy is stored in an inductor. So due to this energy, the device will continue to conduct some more time. What is that some more time? Means that if inductor used in a circuit is large inductor, that will continue to conduct up to pi plus alpha. This is a pi plus alpha instant. This instant I call it as a pi plus alpha. This is a pi. That means if the device, the circuit inductor is large, that will continue to conduct up to pi plus alpha. But the same circuit, inductor value is small. What will happen if inductor value is small? Then you can see that point. As usual, this will be there as such supply. Now, so it will not be continue to conduct up to beta. So that will be only before pi, it will not conduct up to pi plus alpha or a beta based on the inductor value. Now I am explaining if inductor value is less, then it will continue to conduct up to beta. This is the gap. Now we can see that portion. This gap will be present. Now what is observation from this? Earlier, and now you can see in this point otherwise. This one is a, if inductor is large, then what it is started here, where our pi 2, pi 3, pi that point, it is continue to conduct up to next pi plus alpha. No, it is if it is a large inductor. Then you notice here the difference. What is this gap? It is unable to conduct that much duration because you have only less amount of energy. So because of inductor value is small. If inductor is small, then what will happen? The energy stored in inductor is less, and to dissipate that energy through the thyristor, same thyristor with less time. So it is started conduction same as the supply voltage only in the output, but that much up to pi plus alpha duration it is not maintained, but it will be turn off somewhere here before pi plus alpha. That means that instant I call it as a beta. Now beta to pi plus alpha, what will happen? No device will conduct because already T1 is turn off at beta. T2 will fire only at pi plus alpha because pulse is available only at pi plus alpha. That's why you can observe keenly from beta to pi plus alpha, no device will conduct. This we call it as a discontinuous. This I call it as a continuous. So I will show the waveforms. Just this is understanding purpose. Now we can see as usual, only thing is load is RL load. I made it instead of R alone. Now you can use as a RL load. Now we can see these waveforms. Now it will be as a 2-quadrant converter because this 2-quadrant converter it will be operating under first quadrant. It also operate under fourth quadrant operation. I will explain that why we will get fourth quadrant and all. So only the thing is from the wave, quadrants diagram, it is very clear that first quadrant means voltage and currents are positive, and fourth quadrant means current is positive but voltage is a negative. So voltage is negative means that what? Whenever controller voltage is negative and here voltage is negative, current is positive, product what will happen? Negative power. So power is a negative and whereas power is a positive. So what is meaning in that is, if power positive means power flows from source to the load, and whereas another case power is negative means power flows from load to the source. So whatever power is available in the load, that is fed back to the source side. So this I call it as inversion mode of operation. This I call it as a rectification mode of operation. And how this will be achieved, I will explain. So this is a clear cut. Whenever voltage is positive and current is positive, this is the instance of average. Then we'll give as a motoring operation or rectification mode of operation, and this is a negative means positive current and negative voltage. Why current is positive always? Because the thyristor is a unidirectional device, that you remember. This conduction is always from anode to cathode, it never conduct from cathode to anode. That's why it is a unidirectional device. That's why current is always positive. Only if you want to get negative, the device directions you can change, but conduction is always anode to cathode only. Now, this is the waveform. You can see clearly it is a continuous mode of operation, and alpha value is always how much are given, less than 90, no? So wherever I place the alpha, you can see this portion. This is the alpha instant. You want, you can draw the lines also. This is the pulse per T1. Again, this is a pulse per T1. Already I mentioned T1, T2 and all. And negative half cycle, here the pulse per T2. Here you can mention like this. And here you can mention negative. So I mentioned firing pulses for T1, this one, this is for T2. Then how you get the output? As usual, during positive cycle, thyristor T1 is forward by like a resistor operation only, and current will pass like this. Means inductor store the energy plus this side minus this side, and once it reaches to the pi, what will happen? Supply voltage is 0, load voltage also 0, but current is not 0. Reason is some energy stored in inductor. That energy is already plus and minus. Now it will be minus. This is a plus. Then what is dissipation of inductor? From L plus transformer, then thyristor, then R and goes to the L. So like this, same loop will be repeated. So now thyristor remains in the on. So if it is remains on, what is our output voltage? Same as the source voltage. So that we are getting, this is the voltage. Now once it reaches to pi plus alpha, whatever energy stored in inductor is going to be dissipated completely. Then the thyristor T1 will be off. That's why I mentioned thyristor T1 is started at alpha, ended at pi plus alpha. This duration in exam also specify the durations which device is conducting. So now from alpha to pi plus alpha, T1 is conducting. Then at pi plus alpha, what will happen? Remember, at pi plus alpha onwards or at pi onwards, thyristor T2 is a forward bias. Thyristor T2 is forward bias from pi onwards. But why? Thyristor is conducting at pi plus alpha. This one is equivalent circuit in individual instant. Now you can see T1 is conducting. Source T1, it goes to the load. Similarly, T2 is conducting T2 and it goes to the load like that. So given equivalent circuit, if not required, you don't use this also. Just you can use this one and this waveforms. And now at pi plus onwards, T2 is forward bias, but firing pulse is available only at pi plus alpha because we maintain alpha here, no? That alpha has to be maintained. If we change here, automatically there also will change uniformly. Pulses will be generated. Now at pi plus alpha, we are giving pulse to the thyristor T2. So now we are given pulse to the thyristor T2 and the thyristor T2 will start conducting in this direction. Because negative cycle, this is plus, this is minus, it is a reverse bias and conduction. Same, again output will be same as the source. So it we are getting. How long? It will not be turn off at 2 pi. It will turn off at 2 pi plus alpha because of again this inductor is present that will continue to conduct in the same direction. So like that current will start rising up to pi, then the decreasing, again immediately thyristor is conducting, then decreasing. Whether you want to maintain this magnitude or you can start like this also correct. I will draw current waveform like this also fine. Started at 0 because of large inductor it will maintain like this, otherwise you can start 0 getting maximum and then decreases to 0, then rising, then decreasing, then rising, decreasing, continuous only. Here it will go. Yeah. So this is the current waveform. That way also you can do it. So this is the current expression, or you can use this. Anything is correct. Now voltage across the device. Here you can see that peak inverse voltage is a 2 Vm. Reason is what? Why it is a 2 Vm? Now I will show you. Suppose T2 is conducting. If T2 is conducting, I want to measure voltage across the T1. The anode is open in this, cathode is this side. Where it is connected, that voltage is a peak inverse voltage. No, this is anode is connected to A point. And cathode is connected to where? Because T2 is already on, it is also at V. See that the conduction already T2 is conducting the terminals where the anode and there is a switch. You can see here. I want to measure at this point T1. So this point is connected to A point and this point is connected to B point. And here is a total transformer Vm sin omega t plus Vm sin omega t. This is a load. This is equivalent circuit when thyristor T2 is on, this is on, and only T1 is open, and vice versa also same. So this will be A point, this will be as a B point, and what is maximum voltage? Here is a Vm and here is a Vm. Total is a 2 Vm. So because A reverse, just make it as a 2 Vm is a peak inverse voltage for midpoint converter, not a bridge converter. So full wave midpoint converter, peak inverse voltage is a 2 Vm. So like this, you can able to get it waveforms, and similar fashion T2. So this is for RL load. Now same, if you simulate this, this will get it. Anyhow, you can able to do simulation. Given examples and live demonstration also. You try to connect two thyristors and then you can able to show the results like this. And this is for alpha is increasing. Now what will happen if I increase the alpha? Suppose in this case, if I increase the alpha instant, instead of conducting here, where it will conduct? It will conduct, suppose 90 degree if you put alpha, what is your waveform? You will start here and ending at pi plus alpha, no? Alpha will be here. If you put alpha is 90 degrees, firing angle will be here. So then we'll start this point and we will continue to conduct up to like this, and we'll start here, we'll continue to conduct up to like this and this and this. That means this red line is your voltage waveform for alpha is equal to 90 degrees. Because we are moving the alpha, automatically your output will be like this. Then if you take average, what will happen? Positive magnitude is same, negative magnitude is same, average will be 0. But earlier, if alpha is less than 90 degree, what you can get? If positive is more, negative is less. If you take average, resultant will give positive, this much. And once if you keep alpha is 90 degrees, we'll get it as average is 0 because positives, negatives are same. Now, if I increase further alpha, suppose 120 degrees, we'll start here for T1, T2 will start here, T1 again will start here, and like this. Then output waveform you can see will start less positive up to pi plus alpha, means it will continue to conduct up to here, I mean this point, and I will show anyhow results, and this and this. So now the negative portions are more, positive portion is less, then resultant is negative. That is the case I mentioned here. Alpha is greater than 90 will give as a negative output voltage. So I drawn already, you can see here. This is alpha exactly 90 degrees, positive magnitude, negative magnitudes are same, then the resultant is 0. And like this, during this is a thyristor voltage. You can see this conduction interval make it 0 for previous wave, and it is off state same as source, on state will be the again 0, off state will be same as source, like this T1 and T2. Now exactly 90 degrees. What will happen, and beyond 90 degrees what will happen? This is a beyond 90 degrees. What is observation? This exactly means I will start here. This is our waveform, red one. Exactly 90 degrees. Then positives, negatives are same, average is 0. But now I made it greater than 90 degrees, alpha greater than 90 degrees. If you take by seeing itself, see that positive portion is less, negative portion is more. Then average will give negative. That we call it as a fourth quadrant operation. So that is the reason I mentioned there. If alpha is less than 90 degree, average will be always positive, and alpha is exactly 90 degree, average is 0, and greater than 90 degree, average is a negative. That only I mentioned. That we call it as a inversion mode of operation because it is a negative. So voltage is negative, current is positive, and power is negative. Power flows from load to the source. That is inversion mode of operation. And discontinuous, I already mentioned. No, instead of continue to conduct up to pi plus alpha in the previous waveform, I mentioned like this. Yeah, just a minute. It will continue to conduct like this. And for continuous mode, for discontinuous mode, before that it will be turn off. Now current waveform you can see up to beta it will continue to conduct, beta to pi plus alpha current will be remains 0 because no device will be on, and again T2 will conduct up to beta only, and again this point will be 0 and so on. So that means during this small instant no device is conducting. That's why your waveform, current waveform is a discontinuous mode of operation. Whereas previous current waveforms it is a continuous, but now current waveform is a discontinuous. So that is the reason I can mention that it is a discontinuous mode of operation. Now we can see the derivation part. Peak inverse voltage I mentioned 2 Vm. As usual, this is a 2 by 2 pi Vm sin omega t. Expression is same. In case of R load, it will be alpha to pi, but now it is a pi plus alpha for continuous. If it is a discontinuous, what I can write? Alpha will be beta, alpha to beta. So this is the expression. Now from the expression itself, we can easily identify when it will be motoring operation, when it will be as a braking operation, or you can say that motoring and inversion mode of operation. Put it alpha is 0. What will happen? Cos 0 is 1. So what is your magnitude? Vm by pi. Put it alpha is 90. Cos 90, 0. Your output will be 0. And then put it alpha greater than 90 or let it be 180. Cos 180 minus 1. So our magnitude will be minus 2 Vm by pi. So that shows that what? So alpha 0 to 90 will give positive, exactly 90 0, beyond 90 minus. So that's what? Same thing. So it is a discontinuous mode, alpha to beta. Continuous mode means alpha to pi plus alpha. So this is the expressions you must remember. In the problems also we need to solve only direct formula substitution only. They may ask that what is the average output voltage? Alpha is equal to 35 degrees. And input supply voltage is 220 volts 50 Hz. Then how will you submit? Here I know the supply voltage 220, then 2 into Vm. Vm is root 2 into supply voltage into 220 by pi into cos alpha. What is alpha they given? Alpha is suppose 45. That's all. That will give as a average output voltage. So like that your sub problems you have to do it. So once if you remember the logic waveform you can easily draw. Once if you know the waveform, derivation is nothing. Wherever it is started, wherever it is ended, that is a lower limit and upper limit, and integrate will get it as a waveform expression. This is a discontinuous case, that one is a continuous case. So this is the relation between output voltage maximum. Alpha is 0 means our expression is what? VDC expression is 2 Vm by pi no into cos alpha, pi into cos alpha. So therefore alpha is 0, 2 Vm by pi. That's why I mentioned maximum. Then alpha is 90 degrees 0, alpha is 180 degrees minus 2 Vm by pi. So gradually voltage will be dropped down and reaches 0 and develop negative. So this I call it as a first quadrant operation. This I call it as a fourth quadrant operation. So beyond 90 degrees is a fourth quadrant and below 90 degrees is a first quadrant operation. Like this we can able to explain. So we'll see the next class. Any doubt you ask me. And one more announcement in the next lab. From next week onwards, lab sessions are going on, and what we'll do is I already shared in the LMS server lab manuals, Word documents, but now today evening I will share the PPTs also for cycle 1 and cycle 2. You must write this cycle 1 and cycle 2 experiment in your observation before coming to the lab. At least first you complete cycle 1 experiment while you are coming to the lab. Hardware experiment. So cycle 1, 7 experiments, cycle 2, total 7 is the hardware 3 is a simulation. So in that, cycle 1 is 5 experiments, cycle 2 is 5 experiment. I will give total PPT, circuit, tabular column, waveforms, everything. You must write cycle 1 experiment in observation. So circuit waveform in the left side, and then procedure, formulas, all these things you can make it as in the right side, and then model calculation also you have to do it. As per normal observation procedure, you can write the observation so that it is easy for you to do the experiment in the laboratory directly, because I given all the manuals. Cycle 1, cycle 2 PPTs directly. I am sharing you PPTs. Whatever it is there in the PPT, you write it. But in that, for your understanding purpose, I made it as a screenshot of your experimental kit. That is not required to write in the observation. That is only to observe how to give the connections and all. For because when you are there in the lab, it will be there in the kit. Otherwise, it is not possible to see. No, that's why I given as a screenshot of your experimental. Suppose half wave rectifier or full wave rectifier or SER characteristics are given as a kit diagram screenshot. You can see that diagram also before coming to the lab. So it is easy for you to do connections, all these things. If you have any doubt, you ask me in the lab. I will be there in the lab in the hardware setup. You try to prepare the procedure, all these things, read once and twice and come to the lab. So it is easy for you to do the experiment. So now without observation, it is no use to come to the lab. That's why everyone write the observation at least first cycle. And I will share that PPTs in the afternoon. Everyone, you can already I shared the Word documents of manual that will be used for the theory and all. It may be there. You can write in the record purpose and all. But for observation and record also, whatever I will share the PPTs in the PDF form, you just copy in the observation book. And if you have any doubt, you ask me. If you don't have doubts, you can leave.